Cool. All right, so we got a number of attendees. So everyone, I'd like to introduce Andrew Bunnie Huang. We actually went to high school together many years ago. You graduated early, went off to MIT and started doing your amazing stuff. And have had a lot of interesting projects along the way. Many of them have focused on using open source hardware and CAD tools and things like that. So we're eager to hear kind of some of your experiences. And I'll plug your book if you don't plug it yourself. He had a interesting book that came out last year about your adventures in Shenzhen, kind of, you know, going through and prototyping stuff. And it's a really good book. So,
yeah, right. The hardware hacker. That's right.
Yeah, the hardware hacker one. So yeah, that was a fun book. So anyways, yeah, I'll let you take the floor.
Cool. Yeah, thanks. Thanks for having me. I guess you know, Matt asked me to sort of talk a little bit about my experiences with open source FPGA, EDA tools. I call this a brief yet opinionated overview because I guess typically for an academic presentation, you would try to strive to be very thorough and talk about all the different things and like bin them and categorize them. In this case here, this is more just my experiences, what I think about it, and sort of how I bumble around on it. So I don't claim that this presentation is academically comprehensive, but I think it'll go deep enough into a set of tools that give you a flavor for things. So that being said, I embedded QR codes here. They all should be correct. So if you're following along with a mobile phone with a QR code reader, you don't have to type in the URLs. In case the presentation gets a little bit hard to see or the video resolution isn't very good, you can take a moment here to download a copy of the presentation. This very one should be uploaded on my server right here, bunniefoo.com, Bunnie open FPGA.pdf. If there's a problem with that link or someone's complaining about it in the chat, let me know. I can't see the chat view, but I'll just leave that for a second. And also my Twitter handle's down there as well. All right, hopefully people had a chance to grab that URL if they wanted. So we'll get started. So let's first talk about like what a prototypical, what does an EDA flow look like? So this is sort of electronic design automation. Typically, I've drawn in here in brown sort of the two things that the users put into the flow. So design entry, that's the actual writing of your code. And you also add some metadata, some constraints to sort of say where the pins are and what the timing needs to be. And around that is a flow that oftentimes consists of pulling in IP, which comes from various sources, perhaps a vendor, perhaps the cloud. At the design entry stage, you'll cycle through simulation. And then there's a sort of like kind of ladder we go through of synthesis, which turns the HDL into sort of more of a netlist. Place and route, which then takes that netlist and maps it onto the actual hardware itself, the actual locations in FPGA. And then once you've done that place and route, it translates to a bit stream, which is the actual binary data that you would blow into like a ROM adjacent to your FPGA or something like that to load it in. And then finally that drops out to hardware. And then oftentimes you close that loop through a set of analysis tools. So if you're not meeting timing or if you're not meeting area constraints or it doesn't fit, then you do some analysis and pop back to the design entry level and repeat that loop again. So that's what like a very typical EDA flow would be. So the current largely status quo is that we have closed tool chains for this. So basically you have, you know, vendor X, and they will provide for you a set of IP locked to the FPGA, a set of simulation tools that are specific to the FPGA, synthesis, place, route, analysis, all of those. And then, you know, sure, you could use, you know, Emacs or VR or VS Code or wherever you want for design entry, but that's kind of a really minor point. And then vendor Y would have a parallel ecosystem for these types of things. So there's really, you know, there's very little crossover between the two. And so you get a lot of lock-in into the typical tool chains based on the device ecosystem. So this benefits obviously the vendors because the designers are kind of forced into a type of loyalty to that tool chain. So emerging now is a kind of open source FPGA tool chains. So if you imagine here, the idea is that you have now more of a platform neutral set of IP up top, it can be, it typically tries to be cross-platform, although it can have specific bits for the elements of one FPGA or another. But there are ways to handle sort of multiple instantiation to multiple targets by detecting the type of FPGA during synthesis. Design entry and simulation happens there. I mean, there's no particularly good reason why it should be locked into a vendor, other than the really good models that vendor may give you for the specific hardware. But simulation oftentimes can happen at on a third-party basis. And then the synthesis and analysis tools that can happen in the open source domain. And then it can then break out from that point, perhaps into specific tool chains for the place route, bitstream, and the different FPGAs. So kind of the advantage of this type of a flow is that you get a single IP base to learn, and then you can target your favorite FPGA, everything from like a Lattice to a Xilinx to an Altera or something like this. You only have to learn one set of front-end tooling, and then you can basically port the IP to different devices depending upon the power, the performance, the cost, the density that you can get out of devices. So some FPGA hardware families have like really low leakage power, and some FPGA families have like specific DSP blocks built in that you may want to leverage. It'd be really nice to be able to just say, okay, well, vendor A may have an FPGA that we can target with exactly the same code base, and then we can go to vendor B, and if we want a higher performance version but are willing to burn the power, that's just a swap of the hardware and not actually have to rewrite any of the code. And then, of course, and in the very, very long term, you could imagine we could eventually target IC tape outs. So full custom silicon, once you already have the RTL and so forth, there's no reason why it couldn't also plug into the back end that does place and route and GDS2 tape out at the end of the day. So some other advantages of open source is that you get a large base of diverse contributors. So you get a lot of IP blocks that are eclectic, different, things that you didn't expect would be there are in there. So that's kind of nice as opposed to sort of just, the palette of IP that's given to you by the vendor. You can actually fix bugs and tools yourself. I mean, it's a kind of a double-edged sword. So you sort of have to fix the bugs yourself in some cases, but oftentimes it's much worse when you have a vendor IP block that has a bug and like the netlist is locked and the bug is there. It's really frustrating. And then your option is basically rewrite the whole IP block to get around that bug or what else, right? So there is some ability you have a little more control and ability to fix things that aren't exactly what you want. There's a best and brightest theory to open source in that, open source code bases can more easily absorb academic and freelance expert contributions as incremental patches or revolutionary changes. People can fork and change things around. And so you're not just limited to the sort of the intellectual base of a single vendor. It's basically the entire world. So over time that can get better. Also, very importantly, there's an alignment of interests. So in the previous slide, we see that these vendors are having closed tool chains and they give the tool chain to you for free, right? For free. But the idea is that they want to drive more sales with the hardware at the end of the day. And what you find actually is the vendor tooling has very little incentive to actually downsell you to their cheaper, smaller hardware SKUs. So when they give you IP blocks, a lot of times when they compile, the options to actually take out bits of pieces you don't need aren't there. So you'll get an IP block and it'll take a huge portion of the area on your FPGA, and you just have to carry that. And if you want to put more in your chip, well, you have to buy a bigger chip, which is great for the vendor, but not great for you. And then also, very importantly, inside the open source tooling, the software bits are really good. So not particularly the stuff relating to the hardware compilation and the place and route and whatever it is, but the continuous integration, the CI stuff, the tool chains, the firmware, the kernel, and the application support's really there. They're pretty spot on when it comes to supporting things like Linux and a bunch of other upper level layers on that. So then the disadvantages of sort of this open source trend, though, is that there's pretty much a constant churn. So there's a lot of people working on it. Everyone's kind of putting in their different thing, and that oftentimes breaks your build. And then you sort of encounter this, well, it worked for me. And so someone will go ahead and change an API for cosmetic reason without thorough regression, and all of a sudden you have like, your build breaking and, you can't ship hardware. The other kind of big problem with open source in general is that, software is kind of provided as is. And that's an inherent feature of all the open source licenses. So generally, there's no warranties provided with the software. And there's a big emphasis of sort of features over reliability. Now, the thing is that hardware can actually be in service for decades, and it's very hard to find a maintainer decades on. And also, there's just kind of this big disparity because the software can disclaim its warranties. There's not any way for you to be like, well, this build broke this piece of hardware, which is actually in another installation. On the other hand, the way the laws are is that hardware actually has lemon laws. Those are an actual thing. If you sell someone a piece of hardware and you brick it within, say, a short period of time of it being received, because they plug it in and do an update, then the customer has a right to do a warranty claim on you, right? You can't be like, well, it broke because someone else's open source software did it and there's no warranty and I can't get that guy to do anything. You have to deal with that. That's sort of your problem to deal with. So this is a big issue, potential issue. Did I see something pop up in the chat in the Q&A?
Yeah, we were going to ask a question. This guy has a good question about, is there an issue that the developers in the EDA world are not actually the users of the tools, and that contributes to the current state of the EDA tool chain, the open source EDA tool chain?
Developers are not the users of the tools, and it contributes. You mean, so in the open source EDA world, so it turns out actually, at least in the open source world, there's very few pure developers who don't also have to use it. But the difference is that there are users who basically use it because it's a hobby, and there are users who use it because they ship the product, right? And so there's some guys who are like, oh, I want to learn about RISC-V, and I've got this little FPGA board, and I'm using it, and I've committed some patches that make it, better for the compiler to target it, right? And that can be, really cool, and you can get a lot of improvements that way. But then, you also have the person who has an installed piece of hardware at a customer site, and someone committed a patch that creates a very subtle corner case inside a wishbone bus transaction, like in the case of two concurrent burst beats and one terminating, the other one crashes and hangs the bus, and you basically don't get until you hit a certain corner case in the bricks device, right? That sort of like regression is really hard to catch, and those are things creep in all the time. And that's a kind of a different kind of user than you would find on the typical developer, because most of the developers are more from the software side and doing it as a hobby project. So the difference is that when you get to sort of like the professional proprietary EDA tools, ideally guys like Xilinx and Lattice and Altera, they have people who sit there and their full-time job is to do the very tedious process of full regression testing on all the IP. Whereas generally inside the open source, at best you get it compiled and it didn't break. And then someone actually putting it onto real hardware and then like vetting it against all the corner cases is much more rare. And so you end up with a bit of a problem there. And this is a little bit different than like the problem with like Stallman and GCC, because the thing is in software, often, when software compiles and you download it, it runs 100% of the time. On hardware, you actually do get real corner cases. So an actual example of the problem is that I shipped a product that has DDR3 memory on the inside of it, and you have to calibrate the DDR3 memory on a bit line basis based upon the SKUs and the yield of the device, right? And those calibration engines, when you actually ship hundreds of thousands of devices, you get to real corner cases. You're falling off the edges of the eye. You have like loop arounds. You have a bunch of issues you have to deal with, and it takes a really long time to capture all those cases. The simulations aren't sufficient to go ahead and capture those. So I actually have like this collection, this curio collection of like weird boards that have corner case memory with FPGA that I can run personally to check this IP. But it's a really tedious process to do that, and there's probably no one else who's doing that on this very heavily developed piece of IP. So that's probably a long answer for a short question, sorry. So at the end of the day, the thing is that hardware is 90% software. And when I say this, I mean that if you buy a product, so when you buy, a cell phone, right? This is just a shiny brick without software. So really, the thing that makes this interesting is the software at the end of the day. And if you look at sort of the amount of headcount and costs for a typical IoT or greater product, a lot of that is in the software. So okay, if you're just doing like a voltmeter, then okay, there's not a lot of software in it. But if you sort of reach the level of IoT or sort of more complex products, a lot of complexity is in the software. And it actually turns out a lot of hardware development is actually writing code these days, and a lot of the end user experience is writing software. So even if the open source FPGA tooling doubles the hardware effort because you have to do more validation on the hardware side, if it has a software effort, you're still ahead by quite a bit. So that's one of the reasons why, despite all of this, I've sort of moved away from a lot of the closed vendor tool chains. About that vendor lock-in. So a little more about this. How it creates a bootstrapping problem for the open source ecosystem. Vendors don't really see an incentive to hop on the open source bus, right? If you have a lot of market share, open source just means other people can move away from your platform for the shortcomings you have in your particular offering, and then maybe you lose a customer forever, right? And sometimes they're very openly hostile to people who attempt to do open source stuff. So really, going historically, the open source movement for FPGA tooling sort of started with kind of a tiny open source project on a relatively obscure chipset. So this is actually a project by a guy called Clifford Wolf called Icestorm. And you can actually visit the website here and have a look at it. Let me see if I can. I'm going to stop the share and pop over to a browser so we can take a look at it. So hopefully you guys can see this now. And so it's a very, it's a bare bones, Web 2.0 website. It's fine, Web 1.0 website, but it's the content that matters, right? So you can see that this is a project where the person has gone through and painstakingly reversed all these different models. He's created a set of place and route tools. He's created a synthesis flow for it entirely. In here you can see stuff like documentations on the logic tiles and the structure of the lookup tables on the inside where the bits go, all this sort of stuff. All this was sort of pulled out through a process of fuzzing and reverse engineering. And this is possible because the lattice parts are actually a bit on the simpler side, and you can write pretty much complete fuzzers that run in a sane amount of time and a sane amount of space to try and pull out these bit formats. Let me bring myself back to the presentation. Hopefully that worked. All right, back to the presentation. If you want to learn more about the process, there's a paper on it. I've linked it here. There's a QR code, it's actually, if you're interested in the architecture of FPGAs and how things work, this is a really good like brass tacks dig into the whole process. So the current modern Icestorm Flow, I include a screenshot here of an example. It's actually come along quite a way. They're now using a tool called NextPNR. And this image here I have on the right-hand side, if you can actually have it run, and it can show you real-time sort of the place and route happening as the algorithm tries to figure out where to put things. It's really kind of cool to watch. And you can see the structure of the logic blocks and all the routing on the inside. And they have a synthesis tool, Yosis, and they have the final bitgen analysis stuff up the back end. So one of the sort of interesting things is that I think they've tried really hard to extract the timing from these devices, but I still suspect that I'm getting some odd corner cases that don't work because a lot of it had to be pulled out from vendor files and reverse engineered, and there may be it's a really subtle thing to try and figure this out. Particularly, you have to deal with the fact that when you go through multiple nets, you have to go through multiple switch points, and each of those is like a pass gate, and each of those have a resistance that can corner to a different set of corners. And there's a empirical model you have to use to try and figure out like what are we going to model that at? Because if you say, let's assume that all the switches are in the worst case corner, then you're going to be pathologically slow in your result, and it doesn't work. And so there's an assumption that's sort of built into these vendor tools that deals with that. I think is really hard to pull out, and I think there are some, you know, in some cases I've noticed some problems, but you just recompile it and it usually works the second time around. Now new platforms. There's another question here that popped up. This looks like the same question. So the Symbiflow now, which is sort of extending to new platforms. This is we can visit that URL shortly if we need to, but basically the idea of Symbiflow is to take Yosis, which is the synthesis core, and then extend it beyond just the lattice FPGA. So there's X-ray, which goes to Xilinx, Trellis, that goes to the ECB5, and then I think they have an extension also to, let's see, the next one. Yeah, also to QuickLogic as well. So you can sort of see here the device support that they've got. They've actually pretty much figured out everything in the Lattice series. Xilinx is still kind of a work in progress. You can do some basic stuff in it, but nothing beyond a certain level. And then QuickLogic, they're also moving along. And so this Symbiflow project is looking to sort of become, as they would say, the GCC of FPGAs. Let me pop over to their website here. We can take a look at that. Share this screen here. Shoot. Is this? I can't get that out of the way. So yeah, for example, Symbiflow has defined a like this intermediate language FPGA ASM FASM format, which is kind of cool. And you can sort of you can actually take a bit stream and sort of decompile it now to this FASM format, and then modify it, and then reassemble it and stick it back in. So if you have a bit stream that you want to edit after production, you can use this tool to go ahead and do that. It's come along quite a way, but there's still some shortcomings. Let me see if I have. And so I'm going to talk about Project X-Ray next. And so Project X-Ray is the project specifically to reverse engineer the 7 series. And it's a really big project. It's a fairly you know, the structure of the 7 series is more complicated. So they have a lot of documentation here, a lot of unit tests they've written to try and pull out all the different you know, hardware features that are built into this device. And let me see if we have any sort of interesting graphics to show. Usually there's some pretty cool graphics built into here. Yeah, these are just tables. Anyways, you can browse around on the site if you want to find out more about it. But that gives you an idea of the current status of that tool. Okay, I'm back to the presentation. And so because they haven't fully extracted the bitstream format, they can't get NextPNR to work with everything you want to do. The current sort of work is to take all the IP from the open source domain and describe, which is described in Python FHDL. We'll get into that. Compile it to a really large Verilog file, and then feed that into the Xilinx proprietary toolchain flow, like the Vado or ISE. And that basically works pretty well. And that's the tool chain that I've been using the most. In terms of simulation options, you have a bunch of open source options to go ahead and work through your netlist. There's Verilator. It's a fast interactive simulator. It's kind of cool in that you can sort of hook it up right up to like QEMU, so you can emulate a CPU and software, so you can do full software hardware co-simulation. You boot your Linux CPU on simulated entirely, and then you have a Verilog model of peripheral that's being driven by register writes from Linux, and you can go ahead and see how those two interact and capture problems with that. One of the kind of problems with it, as far as I understand, is that it doesn't handle indeterminate values like X's and Z's. It's very fast, but it's not a full, complete Verilog spec sim. So there's also iVerilog, which is it's slower, but it's more complete and handles all these sort of corner cases, which is important to handle for a lot of debugging, like the really niggly bits of hardware. And there's CocoaTB, which is an HDL agnostic framework for manager test vectors and test cases. So people who are developing USB stacks and so forth, are writing these really pretty awesome test benches now to go ahead and work all the corners inside these very complicated protocol specifications. And also, this is the simulator I've been using the most recently. This is actually the Xilinx proprietary XSIM simulator, but it can plug directly into this Toolflow as well. And this here is an example. I've got a full Vextris 5 CPU booting with peripherals, and you can run it at something like 10 kilohertz or whatever it is, 10 kilo instructions per second, which is enough to boot into the bootloader and test hardware, actual hardware using code loops as opposed to writing a bunch of test bench scaffolding to simulate the CPU. There's in terms of the HDL options, there's a large group of people who still use Verilog, and there's a group, a website called opencores.org you can go to that actually you can download Verilog and VHDL IP that comes with various licenses and various capabilities. But the area that I've been focusing the most on has been using Python as an HDL, so it sounds a little bit weird, but they call it, it's actually, you're not literally writing Python code and compiling the hardware. What you're doing is you're describing hardware as fragments of Python data structures. So they call it a fragmented HDL. And then it goes through a process of finalization, which turns it into an actual Verilog file. So in practice, we're going to kind of work through a couple examples of this. We'll look at what's called Migen and Litex on the 7 series. I've got a question here in the chat. Any opinions on BlueSpec system Verilog? I don't have particular opinions on it. We do use system Verilog, but it's another module we can plug in. I haven't actually done a lot of work myself with BlueSpec system Verilog directly.
Going forward, I'll keep an eye on the questions and ask you if there's good ones. So
okay,
and some of them we may just keep till the end too. So
okay, sure. Yeah, every time a question comes up, a little thing pops down, so I don't know if I was supposed to. Okay. Anyways, good that you're on it. So. So there's actually a paper that gives you all the nitty gritty on what it means to be a fragmented HDL. You can go visit it and read it if you want. It's called Migen Litex, and and basically Litex is a framework built around Migen. So if you were to imagine the combination of GNU Linux, so GNU has the C libraries and GCC and sort of the bits, and then Linux is built around it. So they say GNU/Linux. The analogy is that to sort of Migen Litex, right? So that sort of explains what those two bits are.
So there's actually one good question. Have you looked at PyRTL from UCSB, or I guess there's a couple other things in addition to this fragmented HDL?
I have not looked at those actually. Yeah, sorry.
Okay.
I have not looked at those. So I've been spending most of my time in this one particular framework, which is why this is a brief yet opinionated overview. So, I guess, one of the questions is Python as a hardware description language, sort of really seemed foreign to me. When I talk to Python people, they get really excited about all the things you can do with Python. I find the reality to be a little bit more daunting than as it's been pitched to me. There's definitely a lot of sort of spots where I've had to deal with the quirks of Python. But that being said, it has some real strengths. So I did a runoff a couple years ago where I took a design that has a DDR core and an HDMI interface on it. And I built it in Vivado using its sort of system level tools, the vendor specific tools to create it. And I built it in Litex using its native IP. So in Vivado, it took 85% of a 7850, and it took 30 to 45 minutes for it to do a single compilation pass. Litex, which again is compiling with Vivado, so it's the same compiler, but the IP is just different for it. It takes 20% of the same device, and it would compile in 10 minutes of runtime. And it also included a soft-core CPU, which the Vivado Flow didn't include. So I got a CPU for free in that. So you can You can actually, I wrote a little blog post about this at the end of the day. You can get more detail there. And so this is that point about sort of the vendor conflict of interest. So Vivado is free as in beer, but the thing is if they can get you to produce larger bit streams because you're getting all this cool IP and you want to use it, and you have to upgrade your FPGA type, they can sell more expensive silicon. So it was a little bit frustrating. It was a pruning exercise, for example, to use a Vivado flow. There was like, just as an example, and they had these AXI buses that they're using on the inside, and they would include slave interfaces that you didn't need. They weren't connected to anything. You actually leave them unconnected. And when you dug into the hierarchy of what came out, those slave interfaces were just fully there. They weren't optimized out. So it was carrying around large blocks of logic that wasn't even connected to anything that was coming out. And so the good news for that particular piece of IP, it had generated intermediate VHDL files before going to these encrypted blocks that I couldn't do anything with. And in the intermediate VHDL files, I could then comment out the blocks, and then it would compile and run just fine. So it's actually really easy to actually eliminate those blocks. It wasn't a technical issue or a difficulty issue. They were just sort of, I mean, why would they want to do that? They're going to sell you a bigger FPGA at the end of the day. But, you know, me being in a position of shipping real hardware to real customers who are going to pay actual money for it, if I can cut $30 or $40 out of bill of materials, that's a huge amount of margin on my side. So for all the quirks and difficulties of using the Python flow, I was like, okay, this is probably worth digging into a little bit further. So let's talk a little bit about sort of this whole idea of mapping Python to Verilog. If you have a piece of logic, typically consists of stages of combinational logic, those are little clouds that say CL in it, and then registers and combinational logic and registers. That's sort of how all logic is composed. Cycles and stuff also exist, but this is the basic idea. The idea is that you describe the combinational logic in an array called the comb array, C-O-M-B. So they have your self object, self.com, and you keep on adding terms to it that describe all the combinational logic. And you have a synchronous array, which is sort of where the synchronous elements go, and you add those nets to the sync part of the array, right? And you build these Python objects based on the self, you know, so you sort of root, and then eventually you can turn that into a piece of Verilog. So when you go ahead and do what's the finalization process, you basically say, okay, in Verilog, I'll do an OS at star, which means I'm sensitive to everything, means this combination will begin. And I take each one of those combination lines and I do an assign blah, assign blah, assign blah, assign blah. And then under the self.sync, I just wrap that around an OS at pause edge clock. And I go ahead and I do my, you know, little non-blocking greater than equal operator. And then that gives me all of my registers, right? So taking a bit of a closer look, this is going to get, we're going to get a bit into the weeds here, a bit of code. We're going to look first at sort of how do you blink an LED? And I like to say every journey of a million lines of code starts with the LED blink. Like, it doesn't matter, you know, what new system you're bringing up. I always start by flashing LED. I don't know, if I acknowledge it's going to get a little bored, so I put 2 QR codes here. If you get really bored, you can go watch a video of a guy building a house by hand or turning any substance to knife, whatever it is. But if you can, please bear with me. So I put the code online. It's in my GitHub here. You can go ahead and scan that if you want to look at it directly. But here is an example on the left-hand side of what the Python looks like, and on the right-hand side, what the Verilog output looks like as generated. So this is, in this example here, I've written out everything, all the little gory details. So you have like you have an array at the top where you describe your IO pins, the pins they go to, the IO standards. And then you go ahead and you create a class Blink, which is inherits module. And then there's a bit of, you can kind of almost ignore these. These are mostly here to sort of get around some of the build system weirdnesses because I don't have the SOC here. But then you get here, okay, I create a clock domain. I assign, see here, the self.com operator. I go ahead and add the cd sys.clock to the platform request, which is actually grabbing the clock 100 pin here. I create a counter, which is a signal 26 bits wide. I create a sync module. I say counter equals counter plus 1. I create a COM, and I say, okay, I'm going to assign the output of that counter to the LED, which will make the LED flash at some humanly perceptible rate, because we're dividing 100 megahertz clock down. You go ahead and you pull this into Migen, and it creates this Verilog on the right-hand side. That's the exact Verilog that's inferred from this. You can see, okay, here we go. I have the arrows. You can see that the self.sync here ended up inside a pos edge sys clock, exactly as you'd expect. Counter, it's counter plus 1. It automatically decorates the resets for you. You didn't have to talk about that. That was implicit with the language. And then the stuff inside self.com gets pulled out here. So we had the self.com here, the clock assignment, and a self.com of the counter assignment, right? So that's a really simple example that shows you sort of how those two get connected together. So let's get a little more complicated, and we can add a button. So we want to synchronize the input, and we want to extract the falling edge. So this is what that code looks like. There's another branch on this tree here. You can see I've added here a description of a button. I've added a pull up to it. You can do that. These are sort of like vendor specific annotations you can add. It won't port to other devices, but you can get around that by putting sort of if else statements inside your Python code. And I've cut out some of the other stuff on top that is boilerplate, but here you can see that we've gone ahead and we've created a special called a multi-reg. So we're pulling in an IP block that does the synchronization, right? And we go ahead and we create a register, and we go ahead and we compare that with the inverse of the previous state to go ahead and extract an edge. And then we do a little bit of thing here where we reset the counter to 0. And so then here, let me see. Okay, so here we go. We can see that the sync blocks here went ahead and got inferred on this side inside the OS at pos edge sysclock area. So you can see sort of how that mapping, that finalization happens, that fragmented finalization turns into the code. And then all the separate self.com, which were added to the array, got stuck up top in these assign statements. So you can see the sort of one-to-one correlation between the Verilog and the Python. And then this little specials thing, the multi-reg, went ahead and exploded itself into some application, some platform-specific annotations, a pair of registers that goes ahead and gets into the clock domain and an assign statement. And so this is another feature that's sort of built in to sort of make things a little easier for designers to do with. So now clocks, right? So we had a self.sync, but what if we have more than one clock, right? This is a thing that really was not obvious to me in the beginning. So it turns out to sort of specify multiple clocks, you add a suffix to self.sync for disambiguating clocks. So here is an example where we go ahead and we add a slow clock domain. So we have two clock domains we've defined. One is CD sys and CD slow. And here we do self.sync.slow, and that puts everything inside this array into the slow clock domain. This is the blue highlighted region. And we have self.sync, all this goes into the sysclock domain. And actually it turns out that, and kind of one of my beefs with the language is that if you don't specify clock domain, it implicitly drops it to the sys clock domain. And so there's a lot of this implicit, everything goes in this clock domain. So if you're not careful, stuff falls in the clock domain, and you didn't mean to do that, and it doesn't come out until you're digging through a lot of simulations. But anyways, this cleanly turns into, you can see this blue region turns into this blue region over here. We have an OS at pos edge on the slow clock, and then this sort of orange region here, we have the OS pos edge on sys clock, and these two clock domains are inferred accordingly. So not only can this do simple statements, you can actually do more complex stuff like finite state machines. So here's I'll give you a short example of that. Here's a button debouncer, count to 400 in a clock domain, in a slow clock domain. We're going to use a clock domain renamer to put the FSM into clock domain, and a multi-reg to sync the button into the slow clock domain. So this is what this piece of code looks like here. We've created the two clock domains up here on top. I hope you guys can see the cursor going up and down. Otherwise, it's going to be like really hard for you to follow.
Yes, we can.
Oh, good. And then so here in this blue, the actual thing that creates the FSM is FSM, and you can optionally specify the reset state. And if you actually eliminated this clock domains renamer decorator, it would automatically put it into sysclock domain, right? But clock domains renamer, you can actually hand it a dictionary of sort of take this clock domain sys and turn it into slow. And so, for example, if you have they have an IP block for FIFOs, you have a read clock and a write clock. What you would do is you mandatorily have to map what the read goes to sys and then write goes to slow or something like this. So this is how they deal with sort of changing clock domains on IP blocks. And then below here, you can see there's some boilerplate to bring in the buttons and so forth. And now we create a counter, which is a signal. And here we didn't actually have to say what the bit width is. We can just tell it the maximum value is 400 and the reset value is 400. And it'll just figure out what the bit width should be. That's kind of nice. So that way, if you make a design change later on after 4,000, you don't have to deal with updating all of your bit widths down through the file. It handles that for you. And then here we enter, you add states by doing the name of the FSM, which is example, .act, so there's a method on example, and then the first argument is the state name, and then there's a list of sort of things that you will do in that state. So you can say, okay, the next value for button press should be 0. If button is pressed, then next state is debounce, otherwise, and at the same time set the counter at 400. And then we have a second state here in debounce, where we go ahead and we sort of wait for the counter to go down, and then if it's let up, go back, and so on and so forth. I didn't test any of this, so there's probably bugs somewhere, but the idea is you can see what the two correspond to each other. So one of the cool things is that they have this next value function, and so when you call next value, it doesn't make it just assigned immediately in that state. It'll make that value sticky through the entire state machine. So it automatically infers, and this arrow pointing to the right-hand side, the actual state, and then also sort of a chip enable, a write enable for that particular thing. Then you can see that here the case statement for the state machine itself here has been inferred as I've added the states on the left, so it looks really nice. It's pretty clear. And then a little bit further down in the code, it actually creates the clock domain. This is the FSM evolution statement, and then here is the control set for making sure that the counter only gets the counter value when it's supposed to get it, and you've called it on next value. So that's kind of cool. You can do FSMs in this language as well. You can do, I guess, for lack of a better term, Pythonic modifications. So you can actually hack those data structures in a meta way. It's useful for large and repetitive computations, but it makes code really hard to read. So here's an example here called Pythonic Baroque. And the idea here is that we're going to create a delay line. We're going to take several flip-flops and we're going to put them end to end, 5 of them, in fact. And so here I've created a loop for I in range 5. I create a signal. I assign that signal inside the sync domain to S. I do S equals next, and I go back again. And this here looks a little weird because it looks like I'm overwriting a value, but it turns out that because of this plus equals, it's actually adding it to an array. And the fact they all have the same name gets resolved later on. I'll show that. And then here is another example where instead of doing, actually, here we go. This is better. This shows you where things go. So instead of writing self.xor 0 equals signal self.xor 1 blah 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 self.com, this very repetitive thing, you can turn it into, okay, well, I'm going to set the attribute in XOR to XOR plus 0 or 1 2 3, and then I'm going to add to the self.com list the self.xor 0 and make it equal to this procedurally generated counter value, right? So that's kind of cool. And you can see that this translates correctly into the Verilog that you expect over here for that statement. And then this guy here, it works because basically even if you have the same signal, you called it next, next equals signal, and as you add to that sync array, the name itself will be next, but they're actually individual objects that have the name next. And so when they go to finalize, Migen will go ahead and either add like a number to the end of it or add some hierarchical decorators to disambiguate those. So you can see here, it created, blink next 0, 1, 2, 3, 4 automatically from these loops. So this is kind of a nice way to sort of be able to write a bunch of fancy things pretty quickly, but it's actually pretty hard to read, I find. Some Python guys can just look at this and cite it. Usually what I do is I compile the code, go to the Verilog and look at it, like, oh, okay, that's what they're doing. So now this brings me to the final example, which makes the point that actually in practice, no one blinks an LED this way anymore, right? So coders aren't hardware engineers. Generally, when you code, you like to fudge your way to success. Particularly in Python, like you can go in REPL mode and just like dick around with things until you get the right thing and say, okay, fine, ship it, right? In hardware, it takes you 45 minutes to compile something, or even 10 minutes to compile something, that's too long, right? Also, binaries, counters, like clock dividers. Who ever heard of that? What's timing closure? I've never heard of that. And of course, the moment you connect an LED to an FPGA, we immediately need more features like procedurally generated patterns, and we should connect to the internet. Like all these things immediately come in the coder's mind that for me as a hardware guy, I'm like, I don't get it, right? But the way people have done it now, basically everything is abstracted as much as possible in software problems. So if you look at on the internet and you say, hey, I'd like to blink an LED, virtually no one says, okay, get 2 transistors and make a multi-vibrator and stick an LED on it. Maybe you have a bunch of people with 555 timers, but typically it's like get an Arduino and then write the C code and your LED blinks. So, the new age LED blink is to infer a CPU and blink an LED in code. Well, so this is the whole code that is necessary to do that inside Litex. The cool thing, again, about Python is you can import extremely powerful modules. So here's a list of imports you need. And basically, you now go ahead and you call sock core, which goes ahead and you can infer a ROM. You can tell what type of CPU you want. They even have multi-core CPUs now. They have multiple different architectures, toolchains based upon that. You go ahead and you pull in a clock. Here, I decided to just pull in a 12 megahertz clock. We even inferred, here's the clock generator using the MMCM PLL automatically. This will automatically generate the PL with all the arguments and all the loop variables all specified. And then assign that to the sysclock domain. So now I have a nice 100 megahertz clock hanging out. And then I just go ahead, in order to create my LED, I have to create a GPIO. And so here I write another module here, which is my GPIO module. And I specify by this. I say, okay, self to LED equals CSR storage. And then in here, here's my fields. LED state is this, LED pulse is this. And I go ahead and assign the LEDs to the LED pad. And I add that as a CSR to the module. And then inside this ROM, I just put my while one blink function, right? And now I have a blinking LED. Of course, you want some delay so you can see it, but you get the idea. You run compile, you push compile on it, and lo and behold, you get like this huge spew of outputs, which gives you like stuff like, okay, here's my MMCM configs, here's my bus regions, here's all my memory location stuff. And so you can use this to blink an LED. How many gates does it take? Well, the basic blink, the first example we did was 26 flip-flops and 1 LUT, right? And this new age blink is 2010 LUTs and 1500 flip-flops, which sounds like a lot, but it's only about 9.6% of an entry-level 35T FPGA, right, at the end of the day. And so to a first order, it's less than a tenth of your FPGA. You kind of don't care. It's an okay thing to do. In fact, like this is not the greatest sin. So here's I love this sort of little comparison here. I'll drag this aside in case it's in the way. Someone did Hello World sort of in different languages and sort of compared to the size of the binaries, right? And so, in assembly, they're able to get Hello World down to 8.6 kilobytes. And then like Julia is 344 megabytes, Java is 15 megabytes. Rust is 244 kilobytes. I mean, it's just, Python is 15 megabytes, right? So, you know, it's like, so what's 1000x, right, on resources? Moore's law has made 40,000x basically negligible, right? And so the priority is basically on developer convenience over all else at the end of the day. So convenience is all this overhead, about 100x overhead. You get stuff like, you know, integrated code to header flow documentation. So in that Python script automatically output on the lower left hand here, all these header files. That's all created for you automatically. And this documentation here for the register set, it just comes out as one of the artifacts that you can get as part of you know, having used that abstraction of the modules. Kind of cool. The docs can get pretty fancy. So if you scan that QR code, this takes you to an actual SoC I'm developing right now. You know, you can include wave DRAM snippets, so you can have sort of timing diagrams, all sorts of stuff. So, you know, it can be, it's nice to have your fully documented SoC, particularly if you're moving to production. You want to have that stuff. You don't have to spend a lot of time doing that after you've written your code. Another convenience is that the CI integration, continuous integration framework, is pretty easy to do. I say that because I didn't actually have to do this bit. Someone else did it for me. But it seemed like they were able to figure out pretty fast. In this case, we're using Jenkins for our design, and we're actually taking every IP block and running it every time I do a commit and just resimulating everything to make sure we didn't break anything specific to the SOC. It also has integration with Travis and a bunch of other frameworks. It turns out that actually the CI stuff, I was sort of not as big in it earlier, but now that I've seen how the open source development philosophy works, you kind of have to have it, because there's no one doing air traffic control. Someone can do a commit that breaks your language, right? That essentially breaks Litex or breaks Migen. That happens sometimes. And what the CI does is allows the continuous integration engine can pull the latest version and sort of flag those errors ahead of time, so that you're not sort of waylaid by them late in a product release cycle, realizing you have to do a full regression to be on top of the latest version with almost no time left on a release schedule. Other conveniences, huge one, you have community. So if you want to learn more about the sort of stuff here, you can go to Litex Hub. There's a whole bunch of people who've written tutorials and a bunch of IP. There's a regular stream of, I saw good, bad, and ugly new features. So some really cool stuff getting there. Some questionable stuff, some weird stuff that's in work. It's fine. I mean, you know, pull requests are very welcome. You can go ahead and fix them, add things, whatever it is. They target a bunch of boards too. So it's not all roses. There's definitely frustrations. My biggest beef is that Python delivery breaks itself repeatedly. So, you know, 3.6 code may not run at 3.5. Your dev environment sunsets every 5 years, but your hardware oftentimes can last much longer than that, right? And there's kind of no uniform solution to development environments in Python. So there's like Conda and Vumv and pip3 and virtualenv and all sorts of stuff. And then I get, you know, when I complain about this, the Python pros will just be like, well, obviously you should be using an environment. And I point out to them like, look, like the Python docs don't mention this at all. And the tutorial doesn't get to it until section 12 as an afterthought, right? So don't tell me this is something I should have known. You know, I get stuff like, you're running Ubuntu, that's your mistake. I don't understand why that's my mistake, but apparently that's like, they do something with the Python installation that makes it hard for pip to work. I don't know. It's not my problem, but you know, I get that response all the time. Everyone says, you should know not to sudo that. The help message actually says to run this in sudo. So I don't know why people are mad at me for doing that. I recently, the other day, got someone complaining that I was using a version of Python that was 5 years old. I guess I'm nobody then. And then, you know, basically at the end of the day, the Python developers are paid to write Python, and so they assume that you really want to write Python. But the biggest problem overall is that you have hardware that can last way longer than 5 years, right? Like, you know, if you ship a piece of hardware, like you're doing a router or a video appliance or some IoT sensor, whatever it is, these things, you know, I have chumby hardware that's still, I'm doing field requests, support requests on this. It's over a decade since that hardware shipped, right? And so people kind of expect that you can support your hardware for an extremely long period of time. But you juxtapose that against the fact that Python tries to sunset itself every 5 years. And so there's a long-term issue, I think, that needs to be addressed in terms of the release cycles and the durability and reproducibility of the ecosystem. But at the end of the day, the thing is, as I said, products are kind of 90% software, 10% hardware by effort, right? So, even if dealing with all this tooling doubles the amount of effort I have to do to release a piece of hardware, so I have to do all this extra CI, I have to create virtual machines, I have to do snapshots and all sort of stuff to deal with it. If it has my downstream software effort, the overall project itself is ahead by 40%, right? So it's a very pragmatic approach to these types of things. So there is definitely, the vendor tools will be more, reliable in terms of timing closure and a little more by the book when it comes to a lot of meeting the specs. But I think at the end of the day, because the reality is, there's so much value in software these days, going with an ecosystem that gets the software part right can get you ahead at the end of the day for a project. So I think this is almost my last slide, or this is my last slide. So this is sort of open source EDA for FPGA. This particular suite that I've been using is rapidly maturing. There's 4 links to the different sub projects that compose it. You can target multiple FPGA vendors, multiple boards. It's got a diverse and growing IP offering, and it's good for accelerating development. But the long-term support, I would say, is still a work in progress. And with that, I guess I'll open myself to questions. I think that's just about the right amount of time for the talk.
Yeah, we can take voice questions if we recognize your name, or you can type in a question if you'd like us to moderate it and read it. I think Kevin Carplus made a comment when you were talking about Python versions. He pointed out that Python 2.7 is frozen, so maybe we should just use that for hardware.
Yeah, I have this little evil bit of me that says maybe I should just do the eternal Python fork and be like I'm just going to fork this thing and then just lock it in here for a particular, like the Python guys the heads would explode if I did that. But that's
I've run into that. I upgraded one of my projects from like Python 3.4 to 3.5 only to realize that something was deprecated again in 3.6. So it's like, it's highly unstable. But
yeah, which is a big frustration, and that it's one of the not a lot of my other language is Rust and C, and both of those are pretty conservative about language breaking measures, and I appreciate that. Particularly, the big emphasis is that when you're in the business of shipping hardware, you can and will get support requests a decade on, and and you want to be able to pull up a build environment and reproduce what you did 10 years ago and have it at least resemble something of the original netlist that came out. And that's not at all the mindset of a Python person, right? The code you put in a shelf in 2.7 that you wrote 10 years ago, you should rewrite that. Like, their answer is, why are you running that? You should fix that. That is literally their response to me when I complain about that. And I'm like, but I should be able to run my code, right? I don't get it. But anyways.
Oh, here we have a good question. Have you experienced any blowback or retaliation from big vendors for getting around their tools or processes?
Yeah, so far, knock on wood, it's been, I think, a positive thing. Overall, what we're finding is that we're getting more people using FPGAs than ever before because of this. So the hardware professionals, the traditional hardware pros with the big budgets and the corporate backing, I think they basically still buy the vendor tools and they get locked in because it's very hard to change their process. So what the open source stuff has been doing more than anything else is getting more people to use FPGAs and make designs for them. And particularly now that there's some cloud-based FPGAs you can get, and there's a lot of these interesting applications for it in ML and edge applications. I think there's an argument to be made that creating these frameworks will just make the tent bigger as opposed to cannibalizing market share. so long as I think there's a money incentive for them, I think it'll be okay. If at the end of the day, if they actually did see the market like size impact somehow, or they lost a big customer because they were able to move the framework, then probably there would be blood on the floor. But at the moment, everyone seems to be happy because everyone's benefiting.
Yeah. So what's your I give you two different questions. You can pick which one you want. Either what's your kind of next project you're getting excited about, or what would you wish for in the open source framework that's really not there?
I can talk about the project. Unfortunately, the actual I can pull it out here. I don't want to break it. So I'm building a. I can show you the circuit board at least. This is the cool part about being in my lab. I'm building sort of like this secure communications device. This is the chassis frame, mobile phone style, and that's the circuit board for it. So that's the Xilinx FPGA. So if you go to betrusted.io, you can find out much more about this particular device. But the idea is it uses FPGAs have the unique property that you can download the design and you can recompile it yourself. So if you're in a situation where you don't trust the hardware supply chain, it makes it a bit harder for someone to go ahead and hide something inside your circuit board that does something bad to your design, because you can do things like permute the address and data pins to your RAM on the fly with every compilation. So every instance of the hardware is unique. So if someone putting a device tapping on a bus will have to go ahead and deal with that on a device-by-device basis, right? Every place and route puts the cells in a slightly different location inside the FPGA, so you can't just backdoor your silicon by changing a couple transistors, right? So this project here is just an experiment of taking an FPGA, putting it into sort of like a mobile form factor. So I don't have the front on this one; it's taken apart. And then building a communication device and / crypto wallet, whatever you want to do with it. It's open source device that allows us to explore these ideas around sort of verification and security.
Interesting. Yeah, and actually, I know. So that's a board level design. So there's an interesting observation that kind of open source for board level designs, pretty strong right now, right? And then now open source for FPGAs has becoming quite common. It's usable in commercial settings now. Now there's projects for open source in IC design, which are coming along slowly,
right.
Right. So we're now seeing kind of the full span of hardware systems as open source.
Yeah.
Do you think that will change? That's basically influencing projects like yours, right? Do you see further changes?
Absolutely. No, I think there's definitely. I mean, there's a group of people, and God bless them. They're going to tape out open source silicon for even if it's not. Anyways. So the thing is that the hard part on the open source silicon side is actually the physical design kits for the actual transistors and design rules for the metal layers and that sort of stuff. And that there's just, I don't know if you've studied this in your class already, but basically once you get below sort of 130 nanometers, there's like this brick wall where all the SCMOS, the scalable CMOS design rules sort of broke down a bit. And you had to get into these like really funky vendor specific, like, oh, we have to put extra dummy poly around, and then we have to do like all the resolution enhancement. And now you get to really deep sub-nanometer with the FinFETs. It's totally proprietary and crazy. And basically no one's released their design kits, right? So there's been like this brick wall in terms of trying to get into these very modern processes. But you have some foundries that are getting old, right? They still have the equipment, they still run, they need people to do designs of them. And it turns out that in 130 nanometer, it's pretty decent for analog. You can do a bit of digital, not a lot, but you can do a bit. And so, there's a bunch of people who, basically want to tape out RISC-V CPUs in 130 nanometer and get a full open source chip done, right? And I think that's going to be really cool when that comes around. I generally have a theory that Moore's law as a whole, once you've fully depreciated your fab, right, which takes about 3 to 5 years, then the cost to do a new design is just the cost of that mask set. And mask sets are famously millions of dollars for the latest nodes, right? But that's all in value add, right? Once you actually have the machine to write the mask, the actual cost of the mask is the silica for the plates, which is hard to build. They have to be very clean, but they're not actually that expensive. So when you look at older nodes, like even like 45 nanometer, 28 nanometer nodes, the cost of masks is going down, right? And it keeps going down because those foundries who are in the older nodes, they want to reduce the barrier of people making new designs so they can get more business. And eventually, I have a theory that this is going to run into the point where they're like, look, we need a bigger tent. And so they'll be like, look, there's really no more secrets or value in keeping our PDKs secret at 28 nanometer or smaller, right? They're just going to open it up because it makes business sense for them. And then at that point in time, like I think you'll see some really interesting designs start to come up. Because when you get even 28 nanometer sounds big compared to 7, but that's if you look at the space of embedded CPUs like the STM32 series or whatever it is, they don't really tape out at that node either, right? I think they're at 40, maybe they're 28, but they don't need to tape out anything smaller than that. They can get megabytes of SRAM, hundreds of megahertz performance, just fine. This is a huge space of products can be made, I think, in what's considered a relatively old node.
Yeah, interesting. All right. Does anyone else have any last questions? Anyhow, yeah. Thanks for joining us and giving us a talk. I know it's late your time. It's what, 1:30 now?
Yeah, 1:40 a.m. Yeah.
So he told me he stays up till like 4 a.m. So right.
Yeah. Yeah. So
all right.
Now I'm just gonna wind down and get to bed. All right. Cool.
Okay. Thanks a
Good
lot.
luck. Yep. Stay safe.
Okay. Yep. All right. Bye.